The models explaining structure of an atom. The foundation stone for present-day atomic structure was laid in 1803 by John Dalton, who first proposed the atomic theory of matter. He proposed that all matter is made up of atoms. Dalton believed that atoms were the fundamental building blocks of all matter and they could not be split further. J.J. Thomson proposed the model of an atom in 1904, which came to be known as raisins in a plum pudding model. Thomson thought that atom is composed of a dense spherical cloud of positive electric charge with sufficient number of negatively charged electrons embedded in it to maintain its neutrality. The total negative charge due to electrons and positive charge due to protons are equal in the magnitude. So, the atom is electrically neutral. This model was discarded by famous scientist Rutherford. Rutherford proposed a planetary structure of an atom. Shows the experimental setup used by Geiger and Marsden for the gold foil experiment. The basic requirements were a radioactive source contained in a lead box, a lead plate having a hole, a thin metal film, a zinc sulfide screen, and a low-power movable microscope. Now that you are familiar with the experimental setup, let's have a look at the overall experiment. Geiger and Marsden placed the foil at a short distance from the radioactive source, in line with the opening present in the shielded block, so that a thin beam of alpha particles is targeted straight on the gold foil. A radioactive alpha particle source emits particles which are bombarded on the gold foil. The gold foil is 4 × 10⁻⁻5 centimeters thick. The little blinks of lights are scintillations that resulted when alpha particles hit the zinc sulfide screen and are counted in a dark room using a low-power microscope. You can see the path of alpha particles on the screen. Majority of the particles travel straight. Some particles are deflected slightly. Very few particles are bounced back. You can watch the path of the alpha particles in the animation and the particles passing through the gold atoms in the gold foil. You can view the cross-sectional view of the gold foil shown in the animation in horizontal view as well as the cross-sectional view, and observe most particles traveling straight. You can see the large empty spaces in the atom. Few of them deflect slightly. When the alpha particle strikes a heavy positive mass in the center, it bounces back. This positive mass occupies a small area. Only one alpha particle out of 20,000 alpha particles actually bounces back. After the discovery of an electron, the gas discharge tube was modified for additional experiments. In one series, the cathode was shaped like a disc with a hole in its center, and tube's inner surface was coated with a chemical called a phosphor. The discharge tube was connected to a suction pump. Hydrogen gas at a very low pressure was present in the discharge tube. When subjected to electrical field, the tube started glowing red just behind the cathode. Goldstein discovered that this glow was due to the production of positively charged particles produced by a collision between an electron and an atom of the residual gas. This collision knocked off an electron from the atom, leaving behind a particle with a positive charge. These particles were known as anode rays or channel rays and finally led to the discovery of protons. Mass of a proton was found out to be 1.67 into 10 to the power of minus 24 grams. It was concluded after the discovery of proton that electrons have negligible mass. The mass of a proton is 1.008 AMU. Atomic mass of hydrogen atom is 1.008 atomic mass unit. Helium atom has 2 protons. Therefore, helium atom should weigh 2 into 1.008 atomic mass unit. But atomic mass was calculated to be 4.003 atomic mass unit. This showed that mass of a neutron was included, which was equal to that of a proton. Neutrons were discovered by James Chadwick in 1932. He showed that when some light elements like beryllium and boron are bombarded with alpha particles from polonium as radioactive source, some new particles were emitted. Each of these particles had no charge and had a mass equal to the mass of a hydrogen atom or proton. This particle was later coined the name neutron. Let us now learn about drawbacks of Rutherford's model. It was unable to explain stability of an atom, unable to explain the distribution of electrons around the nucleus and their energies, unable to explain line spectra of atoms. As a result, Bohr's model of an atom came into existence. In 1913, Niels Bohr had given a model based on Planck's quantum theory, which is known as Bohr's model of an atom. Postulates of Bohr's model of an atom. Let's take up first postulate. Electrons revolve around the nucleus in certain definite circular paths called orbits. In each orbit, electrons have definite energy. These are also called energy shells or energy levels. These are also located at a fixed distance from the nucleus. These are numbered as 1, 2, 3, 4, and so on, starting from the nucleus, and designated as K, L, M, N respectively. According to the second postulate, the energy of an electron in the orbit does not change with time. This model also states about the energy associated with each orbital around the nucleus and name them as E1, E2, E3 and E4 one after another. The increasing energy levels of various orbits are shown here. While in these specific orbits, an electron does not radiate energy. As we know, energy of an electron neither increases nor decreases in the orbits. These are referred as stationary energy levels. Let's move on to third postulate. Only those orbits are permitted in which the angular momentum of an electron orbiting around the nucleus is a whole number multiple of Planck's constant divided by 2 pi. Now, the fourth postulate is the energy is absorbed or emitted only when an electron jumps from one energy level to another. Emission of energy and absorption of energy is also shown here. Electron is said to be in the ground state when it remains present in lowest energy level. What happens when an electron absorbs one quantum or one photon of energy? When an electron absorbs one quantum or one photon of energy, it jumps to a higher energy level, resulting in an absorption spectrum. At this position, the electron is said to have an excited state. When an electron jumps from a higher level to a lower energy level, it emits energy, resulting in an emission spectrum. The quanta or photons of energy absorbed or emitted can be calculated by subtracting value of lower energy level from higher energy level of the atom. Difference of energy in two orbits is shown here. When an electron present in higher energy level emits photon, it comes to a lower energy level. If energy associated with higher energy level is represented by E2 and the energy associated with lower energy level is represented by E1, the difference of energy will be equal to E2 minus E1. It can also be written as delta E. Difference of energy equals E2 minus E1, that is delta E. This means that emission and absorption of energy occur only in discrete value, which is equal to the difference between two energy levels. It means that energy of the electron does not change gradually or continuously, but changes abruptly as the electron jumps from one energy level to another. Now, let us learn about achievements of Bohr's model of an atom. Bohr's model can explain the stability of an atom, calculate the energy of an electron in a particular orbit of hydrogen atom and hydrogen-like ions. Calculate the radius of each orbit of the hydrogen atom and hydrogen-like ions. Explain the atomic spectrum of hydrogen. Calculate the wavelength of the radiation emitted in transition between orbits. Shortcomings of Bohr's model of an atom. Bohr's theory was unable to explain spectrum of atoms containing more than one electron. The wave nature of the electron is not considered in Bohr's model. As per Bohr's model, an orbital is a clearly defined path, and this path can be defined only if the position and the velocity of the electron are known exactly at the same time. It fails to explain the dual nature of matter. Bohr's model failed to explain the ability of atoms to form molecules by chemical bonds. It was unable to explain the three-dimensional model of an atom.